Hello, everybody. My name is Shuxiang Zhang, and I'm a PhD student from the School of Computer Science at the University of Auckland. So today I'm going to talk to you about the paper titled SLED, Semi-supervised locally weighted ensemble detector. So this is a joint work with my supervisors, Dr. David Huang, Professor Jilin Dobi, and Dr. Yunxin Kong. So this is the outline of my today's presentation. I'm going to first give you a little bit background of the study, and then I'm going to talk about some of the related works. After that, I'm going to introduce the proposed method SLED, followed by the experimental setup and the results. So finally, I'm going to talk about the conclusion and the future work. So as the internet technology advances, more and more data are generated in the form of data streams. So for example, data from social media and video streaming services are all data streams. A data stream is usually defined as an unbounded sequence of data items that are generated continuously by different sources. And data streams also have several fundamental properties, such as infinite length and evolving over time. So because of its evolving nature, so the underlying distribution of the data in data streams may change over time. So this phenomenon is usually referred to as concept drift. As a result of concept drift, the previously trained model in the data streams may become less accurate over time. So in this case, detecting concept drifts can help us timely adjust the model and make it adaptive to future drifts. So therefore, detecting concept drifts in data streams is very important, which is also the objective of this study. So here are some example applications of concept drift detection. So for example, in the case of credit card fraud detection, the task is to classify a transaction as either being fraudulent or non-fraudulent. So we usually train a fraud detection model based on the previous transactions and use it to make predictions about the future transactions. However, concept drift may happen when the behavior of fraudsters changes over time. As a result, the previously trained fraud detection model may not be accurate anymore. So in order to address this problem, we usually use some sort of concept drift detection method to detect when the drift happens. So that, and then we retrain the model so that the model can still maintain a relatively good performance even though drift happens. And based on different classification criteria, concept drift can be classified very differently. Or here we only focus on two different types of drifts, abrupt drift and gradual drift. So this classification is based on rate of change. And most of the existing drift detectors are single detectors. So the problem with this type of detectors is that they may work well only with a single type of drift. So in other words, when there are different types of drifts in a data stream, these single detectors may perform very badly. So this makes us think ensemble methods could be a good solution to the problem, right? So because it can take advantage of the performance of different single detectors in different scenarios. In fact, there have already been many ensemble methods proposed to deal with concept drifts. So however, they only focus on building an ensemble of classifiers rather than detectors. So in this paper, we proposed a drift detector called SLED, which has the following properties. So unlike traditional ensemble method, SLED is an ensemble of drift detectors rather than classifiers. It adopts a local weighting mechanism which can adaptively assign weights to base detectors according to their real performance. Therefore, it doesn't require any prior knowledge of the performance of single detectors. And also, it is robust to different types of drift and does not assume any predefined characteristics for the drifts. So here are some of the most commonly used drift detectors in the literature. And we classify them into two categories: single drift detectors and ensemble of detectors. So single drift detectors are characterized by a single statistic, so which can either be error rate or accuracy. Whereas ensemble of detectors is a combination of multiple single detectors. So SLED actually falls into this category. So now let's look at the proposed method, SLED. So in this method, we made an assumption that some expert knowledge is available to help label some of the true drifts. So with this assumption, we are able to train a set of weights for each of the base detectors in a semi-supervised manner. So the application of SLED involves two stages, training stage and detection stage. So here is a high-level overview of how SLED could perform better than a single detector when both abrupt and gradual drifts appear in a data stream. So in this case, we assume that the single detector can only work well with abrupt drifts rather than gradual drifts. So as we can see in the figure, so the x-axis represents time, whereas the y-axis represents the accuracy of the classifiers, right? And these little circles over here represent different data items, in the data stream at different time instants. And this person over here is the domain expert who labels true drifts and training stage. And this red line over here, shows the change in the accuracy of the classifier with single detector, whereas this blue line shows the change in the accuracy of the classifier with SLED. If we look at the first half of the data stream, where only abrupt drifts happen, we will notice that both classifiers work similarly well in this case. So this is because both SLED and the single detector can handle abrupt drifts very well. However, as we enter the second half of the data stream, the performance of the classifier with single detector starts to drop, whereas the performance of the classifier of a SLED still very good. So this is because the single detector cannot handle gradual drifts very well, whereas since we retrained SLED on gradual drifts over here, so it can still perform really well in this case, right? So next we're going to look at the training stage and the detection stage separately. So this is the schematic diagram of training SLED over one particular training session. So we consider the training process and each true drift as one training session. So this is what happens over one training session. So we've got a training stream over here, and each of the data instances from the training stream will first go through a classifier, and then we will get the classification result for the data instance, where 0 represents the correct classification and 1 represents an error. So these classification results will then be fed to each of these base detectors in SLED to get the detection results. And the obtained detection results will be stored in this result set as a series of triplets. So where ID represents a particular detector, S represents the detection status of the detector, and T represents the time when the detection happens. And based on the information in this result set, we can then calculate two sets of weights. So based on two performance measures over here, the false positives and the detection delay. And then we combine these two sets of weights based on this fusion parameter into one set of weights. And these merged weights will then be adjusted according to true positives in order to get the final set of weights. So we will do the same for the next training session as well, when the next true drift becomes available. So after that, we are going to merge the set of weights learned from the last training session with that from the next training session. So until the final true drift becomes available. Once the SLED is trained, we can then apply it to the test stream and detect drifts. And this is how it works, right? So each of these data instances from the test stream will also first go through the classifier, and we will get the classification result. And this classification result will be fed into each of these base detectors as well. And then we will store these detection results for these space detectors in the buffer. At the same time, we will check the existing detection results as well in order to calculate the weighted sum, right? So these weighted sum actually are calculated based on the weights and detection status of each of these base detectors, right? So if this weighted sum is greater than certain detection threshold, in this case, it's 0.5, and then we will report a drift. Once the drift is reported, we will flush the buffer and start over again. So this is how the detection stage works. So in order to evaluate the performance of a SLED, we used both synthetic datasets and real-world datasets. And we also compared SLED to both single detectors and ensemble detectors, right? And in order to have a more comprehensive evaluation, we actually tested, a SLED based on 6 different performance measures. And here is part of the experimental results. And due to the time limitation, we only included the experimental results for average false positives on synthetic data sets. Other experimental results can be available from the link provided in the original paper, right? So as we can see in the table, so the columns over here represent different detectors, whereas the rows over here represent different data sets. As you may have noticed, for each of these synthetic stream generator, we generated 3 different types of data sets, with 3 different types of drifts, right? And all the best results in the table are highlighted, in both type. And in particular, the best results for SLED is highlighted, in the orange rectangle. Right? So if we look at, the results for SLED, we can see that in most of the cases, SLED, performed the best. So in other cases, even though SLED didn't perform the best, it's still among the best detectors. So as a complement, we also conducted a significance test based on the result in the table. And this is what we got. So basically, what this figure shows is that SLED can actually perform significantly better than these 5 detectors. However, there's no significant difference, between SLED and other detectors. So based on these experimental results, we can draw the following conclusions. So SLED performs consistently well in detecting both abrupt and gradual drifts. And in particular, SLED can achieve better results in terms of false positives, precision, and Matthews correlation coefficient. And in most cases, SLED can reduce false positives even to 0 and increase both precision and the Matthews correlation coefficient to 100%. And in the future, we are planning to add a global weighting mechanism to SLED. So the idea is that, we save the global drifts for different situations. So when a similar situation is encountered in the future, we could just reuse the saved global drifts for that situation, as the initial weights for SLED to learn. So this way, SLED can learn faster so that we can actually improve the learning efficiency. So that's the end of my presentation. Thank you very much.